All right. Well, welcome to the second day of CPP. It's great to see so many of you here. It's my pleasure today to introduce Cezary Kaliszyk from the University of Innsbruck. He has been doing a lot of work in automated theorem proving properties about set theory, working with different theorem provers from, I guess, Isabelle to Koch, HOL. And most recently, one of the things he was an ERC grant exploring really machine learning techniques for interactive theorem proving and automated theorem proving. So with that, I'm looking forward to the talk on improved assistance for formal proofs.
There's only one, I think, or we got only one today. Thank you so much for the invitation. This talk is actually a delayed talk. I was supposed to give it last year, but it did not work out for my health reasons. So it is updated, but the title is the same. So it's going to be the same things, but with just new information that happened in assistance in the last year as well. So what I'm going to talk about is mostly techniques that combine automated reasoning and machine learning to help us produce interactive theorem proving proofs more efficiently. I'll give some very basic things about AI, but we'll continue with things that we know almost immediately. So in the last few years, we've had a huge progress in AI. We're seeing AI winning in this and that game every year. If you go to an AI conference, NeurIPS, every year there is something that is surprising. This year it can be this new card game. This year it can play the game of Doom, which I remember from my childhood better than a human. Last year there was a booth where you could race a car against it and it could do better than humans could do. So we are getting progress in many games, and we believe this can extrapolate to similar games that humans play. And the way I think about theorem proving, the way I am formalizing things in Isabelle in Koch, it is actually a game. It's something where I have some actions that I can take, I can do some things, and I'm looking for my gold at the end. The gold is actually labeled QED or whatever it is in your favorite proof assistant, but we could imagine that AI could win in such a game. And in fact, some of the maths that we see is already relatively hard for humans. I have here the Robbins conjecture, which is one of the first known examples of theorems that humans had trouble proving for several years, and then an automated reasoning system was able to prove it. But note, this was a completely human-designed algorithm rather than AI. This was something that was performed, that was combining things from automated reasoning, from rewriting to actually prove this automatically. This is still too hard for modern AI. Even if this was proved in the 90s, 30 years later, almost 30 years later, AI systems cannot guide the inferences in the right way to do it. Similarly, when it comes to the theorem proving competitions, if you think about something like CASC, there is no real AI going on there. We have some guidance, we have some selection, but not that much is going on. So that's kind of a hint on there's a huge progress, but for theorem proving, it's not that far yet. At the same time, we're having a huge progress when it comes to the large formalization projects. I have here a few logos. I imagine a third of those are things that people in the audience have helped. I'm sorry if I didn't include a logo of yours. I already was out of space on the slide. So the question is, can we actually give some advice for these proofs? Can we actually make some progress there? So this is essentially an outline of my talk. What are the assistant techniques for formal proofs that we could use where we can make some progress? So the first technique that has already been used in many theorem provers over the last 20 years is selection of relevant knowledge. It is already a part of many automated reasoning systems, and several ITPs include techniques that are performing some selection of which theorems could be useful for my goal using learning. And last year we also had a premise selection paper for lean, so it's coming all the time that new things are being developed there, both for new provers and new techniques there. I'll spend some time discussing this. When it comes to the automated reasoning, the way calculi have been designed so far has been mostly manual. So humans are specifying, I am going to perform inferences with this and that heuristic, but you could actually learn from the successful proofs. You can learn this is the way inferences actually can be combined that is more likely. So we can guide provers, perform this guided automation, and this can be done on various levels. I'll talk about this a bit as well. Humans are not usually proving on paper proofs in the same way automated reasoning systems do. If I'm trying to prove a certain mathematical theorem, I'm going to make some intermediate sub-goal and do some kind of divide and conquer. So I make a conjecture that I'll try to prove this, and from this I'll finish my goal. So I kind of dividing my thing in half. And then I have two simpler things, which I'm also going to divide and so on. I'm performing this. This is very nice. It simplifies things. There are no systems that can do this efficiently yet using learning synthesis techniques, but this is also an active field of research, and we can see what's going on there. And at the end, I'll discuss a bit about more direct automation. We have some things going on about more advanced translations, about improvements to the foundations of the calculi that allow efficient automated reasoning, but are at the same time relatively powerful, and so on. I'll talk about this closer to the end of the talk. Okay, so when it comes to the knowledge selection, this is a key functionality for humans, not so much. You cannot make that much progress when you know these 100 things in the library are very useful for you, but for AI ATP systems, for so-called hammers, if you can predict a certain subset of the knowledge that is useful for you, then this can be used for automated reasoning, and this significantly increases the power of automated reasoning. So the goals are being then filtered to predict, let's say, the 1,000 most relevant premises, which can then get translated to some system where automated reasoning works that is going to return the actually necessary premises in an ATP proof, which is typically going to be 10 or 15 or so, which you can then reconstruct back in your favorite theorem prover. I have here a ... I've mentioned the ones where these techniques are working best. This also works for several other foundations, but the success rates are quite different so far. So how does this premise selection, this selection of relevant knowledge, work in comparison with just using a heuristic? So this is how it used to, how it used to look like about 10 years ago, when for the first time we had the integration of a machine learning-based selection in Isabelle. The top success rate jumped from something like 38% to 47%. So this was really a major improvement, and this was using a very simple, naive algorithms, so KNN, k-nearest neighbors, naive Bayes, very basic machine learning techniques. And in fact, those are still the ones used in Isabelle until today. There's no, even if the machine learning people have been writing papers for these 10 years saying, we have a better evaluation, we can do this more and this more, none of these have actually helped the Isabelle theorem prover yet. I'll comment a little bit on this later, but I'll say something about these better techniques as well. So the first experiments with trying to go beyond the syntactic methods using some deep learning for premise selection, those were results coming from the Google DeepMath group, have tried to, in a rather simple way, so I'm going to use the expression in anger, embed our premise and a conjecture, put those into a concatenated embedding, put some fully connected layer, and hope it's going to predict this is useful or not useful. it's a very naive assumption in the sense, as a human, if I'm looking at a completely random theorem without any other ones, trying to guess if this is useful for a conjecture, I will not be able to do the task. So if I, as a human with experience with using theorem provers, cannot predict this, cannot guess this without having more knowledge about the library, this is not going to be something where we can make significant progress. Still, it could achieve similar results to the simpler machine learning techniques, which is cool, that's nice. It requires about, I once counted, about 100,000 times more time. So rather than 2 seconds, you need about a week of CPU time, which, okay, it's absolutely crazy. You cannot use it as a user of an ITP, but it is cool that you can do this. These have been improved in many ways. The most important improvement is the use of graph neural networks. I'll explain graph neural networks only with a very vague image. Of course, mathematical formulas have some structure. They're just not just sequences of characters where you can, based on the characters, predict things, but they have a structure. If you use the information that you have about the structure, you can embed a formula in a more meaningful way. The way this is typically done is, for a graph, the nodes are going to send messages to each other saying, this is my current label. After a certain number of such message passing and performing some kind of convolutions within each node, we can combine the embeddings of all the nodes to get a total embedding of a whole formula. This is the very rough idea of what's happening in graph neural networks, and I'm mentioning this because until today, graph neural networks are the state of the art there. The best method for most machine learning theorem proving tasks. I have here 2 different years, so depending on the task, it is, for some tasks it was already since 2019, for some tasks since 2022. And I'm saying most, there are some claims that transformers works for some things. I'll mention this later on in the talk, so transformers and GPT models. All right, this is nice. We have some way that is completely abstract. It's not doing anything that is semantic. It's just looking at what's happening in the formula. Can we do better? And we can do significantly better if we use knowledge that we have about formulae, about logic. I'll again explain this first in a rather intuitive way. Let's think about something like a self-driving car. When it sees a stop, it has to recognize the stop and say, well, this is a stop sign. That's nice, that's easy. But we can train a network that's going to recognize it. However, if my image is somehow distorted, if it's stretched and at an angle, is it still going to recognize it to be a stop? We don't know. It's even more important if it can recognize, there's a pedestrian, then I'm not going to ride over them. But if the pedestrian is lying, it cannot recognize that it's still the same pedestrian. That would be horrible. And there are ways in computer vision to deal with this, where we can be, with the help of things like equivariant networks and other techniques, we can guarantee that a rotated and stretched image is going to be somewhat related to the original embedding. Therefore, you can easily recognize those are the same things and behave in the same way with them. What does this have to do with logic? We have various natural transformations on logical formulae, and something absolutely trivial is variable renaming. Of course, if I just rename variables, this should be the same formula, and we have techniques for dealing with this. We use the Bryan indices. If we want to use some equisatisfiable things, then we can use things like the Bryan convention. So there are lots of things we can do that we know, and those are easy. But we want some invariance when it comes to connectives. The next talk is going to be about intuitionistic, so type theory. So I will say this is, for example, in whole, where we are going to say that implication is the same thing as negation A implies or negation A or B is the same thing as A implies B when we have classical logic. So then we have some kind of transformation on formulae where we want to guarantee that these are actually the same, even if their graphs look differently. And there are some nice ways of encoding formulae with the help of graphs that allow preserving such relatively simple transformations. And this can be also extended to some other calculi. So this has been done also for Coq, for example. An even further way of going along this property invariance is being able to recognize things that are related. As a human, if I work in a domain that is kind of an instance of a group, I have some ways of dealing with a group. If I have something else that looks like a group, I'll recognize it. I'll try to do the things in a similar way. When it comes to these machine learning techniques, they will not realize it unless you're going to teach them this. So we have techniques of realizing that certain subparts of the graph are similar. And so here, if I have a formula that looks like something plus a 0 and a different one, something times a 1, we have an operation with a neutral element, is going to be realized that these are more related than just sharing the symbol, and techniques used for dealing with these are going to be similar. That's a pretty cool thing, and we can make use of that. Those are the most recent advancements when it comes to premise selection, and that seems to be working pretty well. So this is the first part that I wanted to discuss, this improving premise selection. The next thing I'll talk about is guiding automation. What do the best machine learning techniques for guiding players in games do? I'm going to here present in a very simplified way something like AlphaZero, and I'm mentioning AlphaZero and its variants. I'll focus here on this one as we do not need stateful learning. Essentially, what we need to do is to self-play a certain game using a learned strategy, improve the strategy based on what we've learned from playing the game, try to search the game tree wisely, that is, not explore it in a naive way, and finally estimate moves and states independently. Those are kind of the 4 components of AlphaZero, which was claimed to be winning against humans in chess, Go, Shogi, and a few other games more recently. Okay, nice. Can we do the same thing for theorem proving? In principle, in a certain calculus, we could do this. So we, in principle, have some techniques for automated proof. We have to be careful about the calculus. There are calculi where our branching factor is infinite, so we have to see what happens there. But yes, we can try to play a random game using an arbitrary policy. We can estimate states and actions. This is, again, relatively easy to make a heuristic for this. For example, auto is the tactic that seems to work in 50% of the cases. The other tactic is the one that's most useful here. So we have some simple percentages. We can actually train a model that's going to do better than this. So similarly, we can estimate how close we are to finishing the goal. Let's say how many sub-goals we have is a very simple heuristic. So we can do this. A calculus where this works particularly well will be Tableau calculi, and then we can use things like Monte-Carlo Tableau. What I mean by Tableau, for example, for uses of Isabelle, I mean what BLAST does in Isabelle is going to be a classical instance of a Tableau algorithm. Those were initially evaluated with just first-order Tableau, but now it works also in other settings. And finally, we need to learn from what the games produced, so perform some reinforcement learning. If we were good doing these actions, then we are going to repeat those, and the other way around. So can we do this for a particular proof calculus? Can we do this if I am in a calculus where these are my possible low-level inferences? Or even, can I do this on the level of interactive theorem prover where I have certain list of possible tactics and I can choose between the tactics. It seems to work quite nicely. The most important thing to do is to make this decision which is the best action to take, how to make the decision. So given some of these prior probabilities, these are my actions that were useful in the goal, in similar goals so far. And having done some experiments, I have explored my goal, I tried this tactic, that's what they went. What is the action to take? This problem is again a classical machine learning problem. This would be the so-called bandit problem that originates in the casino. So we have these one-armed bandit machines, a machine where you have the one arm, the handle that you pull, and with a certain probability you're going to win with the help of the machine. This probability that says for this machine this probability is a half, for the other probability the probability is something else, are our prior probabilities. But then we have been in the casino for a while. I don't go often to casinos, but imagine you have been going to the casino already for some days and you tried this machine 10 times, this machine you tried 100 times and so on. And for this one that you tried 100 times, you never won. The probability a priori is still 50% or whatever, 49%, but you never won. So there's something about your prior estimation that is wrong. This estimation is not a perfect one. Based on the experiments, you know that this is the one that you should not try. For the other one, it seems you're winning more. So let's use this more. Let's exploit this more. So which is the one that we should take now? And if I tried the other one and now I won a certain number of times, maybe this was just a random thing that this one was not working. Maybe it's actually better. So I should do both some exploration and some exploitation. So I have my priors. And the priors, I'm going to already go back to the theorem proving setting. The priors are this tactic was successful in similar goals this many times. We have the average rewards, meaning I tried this and that tactic a few times and it came out to lead me to goals that look provable or not. I have some number of experiments and so on. And there's a formula that's proved to be the optimal one that maximizes this. Excellent. I will not go into the details how the formula works, but the important thing is if we apply the formula, we can explore our proof tree in a meaningful way. So here I have a Monte-Carlo proof tree, so this tree search for a Mizar problem. I think this is the only thing which I'm presenting for Mizar. The rest will be about more modern provers, but the Mizar one is useful for some of the initial experiments as its translation to first-order logic is straightforward. Then we have a certain reward that's coming from the actions that were available. Based on this, we are performing some visits in the different sub-branches. The ones that had a high prior are visited quite often, but if the reward is lower than the other ones, then we're not visiting those. And similarly, as we go lower, some of those will not even be visited at all. So that's how the tree roughly looks like. So here is an actual rendered proof tree from a run where it's actually, can I do this? I can. So what's happening is after the first action, we already see that several of the possible things are not explored even at level 2. It doesn't even try it. Its probability seems to be too low, but it is going to find a proof. So here's the blue node. It's going to find a proof at depth about 300 in this particular case. So this is very exciting that we have an average branching factor of 10. And we've been able to find a solution that is kind of at the depth of 10 to the 300. Maybe there are some other ones somewhere not too far, but no other prover was able to solve this one, so that's pretty exciting. So this seems to be both significantly better than best human-designed strategies, and we can also do the same thing on the tactical level. So we have systems that are exploring the tactic space of proving things in a proof assistant. In hole light, in hole 4. In hole 4, the tactic toe system is already integrated in the distributed version, so that's what you can immediately try, and this seems to be the strongest automation available there that does exactly this. It has learned a strategy to explore things based on trying to apply tactics, and then tries to apply various sequences of tactics to find your goal. We have an experimental mode for tactician for Coq, but that's, you need some compilation flags, and so that's coming soon. So yeah, that's yeah. All right. So, and this is not only done on the level of provers that you're running directly in the system, but also if you are you can use this internal guidance provers from a hammer. So that's also something that is still unpublished. We have Enigma for Isabel. So this is a guided version of E, and this guided version of E can prove several Isabel goals that no other prover can. So we can run Sledgehammer with this Enigma, and since this is something that is trained on some part of the repository, we are providing a trained Enigma, so you can do remote Enigma, and you're getting a solution that no other prover could find. That's pretty nice and exciting, and we're hopefully getting some of these guided provers helping ITPs soon. Okay, next thing I want to discuss is communication with a proof assistant. It's clicking me. The way you are interacting with a proof assistant has this relatively idiosyncratic way to it. If you've been working with one for some years, it's nice, you can understand it, you can write things fast. Still, things that you have done 100 times, you have to do them again. It does not seem to understand very basic things. If always after you introduce a variable before elimination, then you are going to generalize something, that's something that always makes sense, it always improves things, but it doesn't know it. You have to do it, or you have to implement the extension. Implementing an extension, there are some things that are nice in proof assistants that help you do some extensions. Some of those are relatively easy, things like LTAC or Eisbach that I imagine several of you have tried and done. But when it comes to actually implementing an Isabel package or implementing an Coq ML4 extension that is going to be a module that's compiled in Coq, I'm actually going to make a poll. How many of you have implemented an extension of your favorite prover? Okay, I have 4 hands in the room, 5. That's what I would expect in an audience like this. Still, this is something that is significant work, and I am not going to do this for 100 times. But if you are interacting with a student, if you're interacting with not even a master student, if even a bachelor student who you ask to formalize something simple, they're going to realize in this situation I always do that, and they're going to do it after 5, 8 times. They'll see the pattern. They're going to be more efficient. So could I have a better communication with a proof assistant? Could I have some predictions of actions that are going to be more efficient? So that's part 1. Part 2, can it already help do more? That is, if I have something in informal language, can it even state it and make some progress about it? So what I mean more precisely is to have a proof assistant, someone who assists you in interacting with a proof assistant. So given some text, they're going to be trying to understand what you meant, your natural language text, say, what is it that I think you actually wanted to write? So you wrote something about pi. Did you mean the real number pi or the complex number pi? They're kind of the same, but when we're discussing the syntax of a proof assistant, they may have a different syntax to it. So what did I think you actually wanted to write? And does it make sense? What do I mean making sense? I mean, can it be proved? Can I justify it in my calculus with the help of my automation? So it's kind of understand a LaTeX formula as well as some text around it, possibly formulas, but the formulas is easy. Translate it to the logic of a proof assistant or of the proof assistant if we're focusing on one, and report on the success on some automation. And I've discussed a little bit of automations already, so we can imagine we're passing it to a hammer or to some of these tactic-toe-like systems that are powerful now. So can this work? And we've already had some early successes with similar tasks maybe 8 years ago using completely symbolic methods where we're just predicting the possible ways to interpret a term. So if I write a formula like sine 0 is equal to the cosine of pi over 2, then actually what we mean by this is I want the parentheses to be around the pi over 2. If you just drop the parentheses, which is kind of like what I, as a mathematician, would write quickly, everyone is going to be understanding that I do not mean the cosine pi then divided by 2, but rather the cosine of pi divided by 2. But it makes certain predictions of what it could be, and if I can prove it, and for many of them it says, yes, I actually can prove it with the help of my automated techniques. For some, I can actually disprove it. I can say, I am convinced that the negation of this can be proved. In some cases, it has no advice. It doesn't know if it's true or not, but you can still select which one you want. Okay, so that's the state using completely symbolic versions of the task. We have significant progress on the left side of things, so on the way how to interpret formulas as possible expressions in a proof assistant using these transformer models, things like GPT. So if you're going to ask a GPT-like model, how am I going to express this in formal mathematics in Coq, it's going to give something. But this something has absolutely no relation to what is meaningful. It's only syntactically learned. So we have a nice progress on the left side, but lots of issues on the right side, so this cannot be integrated directly with the systems done as on the right side. So why here, when it comes to the prediction, we can already filter out things that do not type check. We can filter out things that do not make sense. You cannot integrate easy type checking in these transformer models. That is actually things that people are working on, and we'll see how far this goes. We have some progress on automating formalization as a whole. Imagine the following sentence, which in the input LaTeX have some representation, the correct formalization of the sentence in a proof assistant. I think this one is from Mizar, but we have the same thing for whole as well, is some representation. If you train a transformer model, essentially a GPT model, around snapshot 7000, you're getting an perfect representation of the statement. And the cool thing is already some of the intermediate representations are equivalent. This is a thing that is quite nice, is that the equivalences that I've discussed before, things like equivalences between the implication and negation, or that maybe is one that is not always desired, but we have some equivalences that would be interesting about the way things can be expressed. And in case of this one, we have different representations of natural numbers. There's a nat and there is b natural, and it finds such equivalent formulations which suggest it has a little bit of understanding of mathematics, but has no idea about actually progressing when it comes to proofs, and that seems to be a pattern for all the methods, all the deep neural network methods. I had a discussion last afternoon with Katia Komendanskaya, and she has brought up these examples that the GPT-based models, so these large language models, are having trouble with basic mathematical tasks, which are basic propositional logic puzzles. Puzzles that are things that we don't need a SAT solver. We have 20 Boolean variables, 20 propositional variables, and very basic sentences that say if A, then B, but if C, then not D, and so on. And models of this kind are still having trouble, and we have whole classes of formulas like this where they completely fail. So we don't have to go to foolproof assistance. We are stuck even on the level of essentially SAT problems and trivial SAT problems, problems where we can do 2 to the n options, and this is also going to be doable in reasonable time. The next part of my talk is going to be about disproof. So my experience, and I imagine it's also the experience of many of you, is that the first time you're trying to formulate some goal, it actually is incorrect. You're going to state your thing and you forgot some assumption, or you forgot that x has to be different from 0 because you divide by x, or something like this. These are relatively minor things, but these changes that you have to make, they are surprisingly common. I'd say it's more often that a statement is incorrect than a correct one. At the beginning, and then when the proof gets closer, then we're happy and everything stays right. For this, it's nice to have techniques that let you automatically disprove things, and we have quite a number of disproof techniques already, interactive theorem provers based on either quick check or SAT solvers. So things like NeetPick are essentially based on tools that are enumerating finite models of increasing sizes. So maze-like finite model finding in first-order logic has been popular already for more than 20 years. However, these are all finite models, and as soon as you include something like the integers, the finite models may not be enough, and the strengths when it comes to finding infinite models are very limited. The SMT solvers are not able to make much progress there, even if the syntax allows this. Are these infinite counter models common? How common are they when it comes to goals in interactive theorem provers? There are very simple things around starvation freeness and pattern examples. So something like an elevator, which you want to make sure that it goes to every floor, but someone calls it on floor 2 to 3, 3 to 2, and therefore it never reaches floor 1, for example. So these kinds of examples, and of course this in some programs, are quite common, or things like even odd, something that just flips the bit. We have examples in algebra, so streams, infinite trees, and so on have been formalized in many provers, and showing counter examples for incorrect statements that require this often requires infinite models. Infinite sorts. Just a moment. Infinite sorts, the way we can express infinity is using a function that is injective but not surjective on a set. In fact, this is the way the axiom of infinity is specified in several whole theorem provers, for example, in whole light, but this is also the foundation of linear integer arithmetic. So we have various examples of this, irreflexive, transitive, serial relations, and so on. So if you look at the hammer problems that are generated, surprisingly often the problems are not provable. Why is this? This is because hammers not only produce things that are directly corresponding to the user's input, but they are restricting the numbers of premises, both as part of premise selection and as part of proof minimization. When you're trying to find out what is actually necessary in the proof, then you are reducing these numbers and hoping this is still going to work. So if you look at the libraries of hammer problems, many of them have an unknown status, and the suspicion is many of them are actually satisfiable, so there's no way to prove them. So we are also going to look at some particular problems there. We've used syntax-guided synthesis. This is a somewhat different field of research where using synthesis we can try to find a model, and the model is going to be a second-order function. So the way we're going to do this is the way Cygos works is given a background theory, something like linear integer arithmetic, or we add equality. We have a second-order variable to synthesize together with a specification and a grammar that is supposed to produce the language. What the solution to a Cygos problem is an expression such that it matches, so this is in the language, and substituting the specification for the expression satisfies our specification. For example, consider linear integer arithmetic. We want to synthesize a function called max2. The name is meaningful, so it's going to be a maximum of two things, together with a specification and a grammar. What is our specification? What do we want about our max2? Max2 of two variables is supposed to be greater than both of the variables, and it's supposed to be equal to one of them. Sounds good, sounds like a meaningful specification. And we have a language, so the set of possible expressions that can be used to express our expression. So this is going to say that an integer can be our variable x, y, it can be 0, 1, plus, minus, if then else, booleans. Similarly, we have a boolean expressions, some comparisons, and so on. This is encoded in a language similar to SMT. I will not explain the details of the language, but it's equivalent to the thing that's written here. And we can translate problems that come from hammers using their SMT encoding into Cygos. I will again not go into the details. Translation is straightforward, but the power is extremely limited. So directly looking at the hundreds of unknown problems, there was one or two that these synthesis tools could be able to solve. So what we would do instead is to define a heuristic for infinite model construction. The way the heuristic was done is we were actually looking at some of these problems and trying to guess what original theorem proving problems they come from. They come from things in Isabelle where the original sets would be natural numbers, integers, and so on. And you need to find what interpretations would be the ones that are interesting for our problem. So we would guess the interpretations for the sorts, check for clues that the sort must be greater than 1 or infinite to eliminate those, and then guess the functions generating the possible trees up to depth 7. This allows to reduce our set, and only with that call Cygos for the synthesis, and then we got quite a lot of success, so we would be able to disprove a few hundred of such problems that have been in the SMT-lib library originating from Isabelle. So that's pretty nice that we have this direct translation of a problem and showing this can be disproved with a certain set of the knowledge. If you increase the knowledge, that is a little bit trickier, but it's very useful for the user to see with all the things that I have in my library, I cannot continue there. So we have here a solution of several things, and we're trying to extend this to inductive logic programming to be able to synthesize several functions. So this is also working quite well. I have discussed premise selection. There are several things going on in premise selection, meaning about both the graph neural networks and on the more logical way. The way the graph neural networks describes what is happening in a formula is completely syntactic. We're only combining the information coming from an embedding with, so the symbols with the structure of the formula and its relation to the other formulas. It has no semantic information. We have already known for maybe 5-10 years that there are very good semantic ways to characterize formulae. In first-order logic, what is the meaning of a logical formula? The meaning of a logical formula is what are the models in which it is valid. So two formulas are equivalent if they have exactly the same models. And the way to characterize formulae is with the help of interesting models. And there are ways to use counter-model finders to find parts of formulae which are satisfied, unsatisfied in subparts of the models, and use these as features. These features are extremely strong. The malaria system that uses those is quite slow because evaluation of formulae in models is very slow, but it is significantly stronger than any neural network models. So that is what is going on, trying to combine some semantic information, some things that know about stronger features with neural networks. When it comes to models, we do not have good ways of extending this beyond first-order logic, but there are other semantic information, things like formulas are going to interact if they have parts that are unifiable, and checking for unification can be done efficiently with the help of first-order indexing structures. So that is what is happening in the first field, and we have pretty strong premise selection at the moment only available in the MES-AR system, but expect that this is coming soon. Better ATPs in hammers. I've been already telling you about some of these guided versions of the first-order provers, but we also have a guided version of E and guided version of Vampire that you can train on the libraries of interactive theorem provers. So these are versions of provers that know how do the ghosts look like, what was useful in past proofs around exactly the same libraries, and those are the ones that work pretty well. For E, this has been actually already evaluated on the large part of Isabel's AFP. We have some more things going on because we have to still extend Enigma to its higher order variant, so that's ongoing work, and there is the work of Martin Suda on Vampire, so that's a similar thing. Large language models, I have mentioned some problems with those. We've discussed with Brigitte that we have the community of people that are working on machine learning from the automated reasoning side is quite disconnected from those doing this from the machine learning side. The reason is the methods for evaluation, the techniques are quite different, and the things that they are able to derive are not particularly useful. We have some very promising things that say, I can do 20% more Isabel than the other models, but it's trained in a way that I do not know if it is consistent. So if we have a GPT model that has seen all of the internet, all of GitHub, where there are 12 copies of the Isabel library, is it really true that it can do this many proofs of Isabel if it has seen this many copies of proofs in Isabel? This is very hard, and there is quite some progress. I cite here some promising research, but there are some that we have to be careful about. They may be interesting from the machine learning point of view, but not necessarily for us yet. The strongest automation at the moment comes from tactic-based proof search. So in Hall 4, we have tactic-TOE that uses this Monte-Carlo tree search to try to, by itself, explore. This tactic looks the most promising, this one is the second, this one is the third, so let's try them all. And now, based on the information, what happened after the running of these tactics, how the state looks like, what's available, is going to choose where to go next. It's going to go there, and then, oh no, this doesn't look very good, so I go back, I try the other one. This is fine, so I go a bit deeper. No, actually, no, I cannot make progress, so I go back. And so it does this kind of exploration with tactics in a way a human, a student, could do this. Someone who has not much knowledge about tactics, but is doing this exploration in a somewhat random way. Those are pretty cool. And the ones that are actually usable with provers are the tactic-TOE and tactician. We have several external tools that are promising to do things. I don't know how well these could be integrated, things like Lean Dojo and so on, they still need some further work, but they might be pretty cool. Where I imagine this is going, so what are the, in my opinion, most promising works in the recent time would be the various approaches to direct automation. Rabe, Wolfgang Betzmüller have proposed dependent whole last year, which is an extension of whole with dependent types. It seems to be somewhat weaker than the type theory that we're used to and love, but at the same time, it lets you express everything and it enables efficient automation. So there is work going on also within my group to try to change the foundations of provers so that we can provide direct, efficient automation for some variants of dependent type theory. There's the whole thing about bridges between foundations. For many proofs, it does not really matter which foundation we're in. So if I look at the library of Koch and Isabelle, there are 50% of the things that could have been done in either of the two, and the idea behind the proof is the same. So why not? So like this is some mathematical idea. This I prove by induction on this number, and then using simplification, using these equations, this could be done in any prover. Can we learn from all the foundations? Can we do things in a way where we have an idea behind the proof and then we actually express it in one of them? So there's, this seems to be working between some foundations. So things like Isabelle ZF, we can get inspiration from Isabelle whole proofs and move things actually using some isomorphisms. This is pretty nice. It would be nicer if we can go to the more useful things there. And the final two things would be some translation tasks and synthesis tasks. I've given some hints. There's some exciting work going on for synthesis of tactics using ILP, using other methods. That's it. Thank you very much.
Great.
No? Ah, yes, now.
Okay, maybe we can
Right.
put the mic in the stand over there. Okay, there's a question over there. And maybe you can say who you are. And
Hi, Cameron Freer. Yeah, thanks. This is lots of interesting stuff. I have a question about large language models. So you mentioned how sometimes it doesn't even produce something that's syntactically valid. But like a common workflow that people have with, say, ChatGPT when programming or even, dealing with nasty installations of things or whatever is to just copy large error messages, including stack traces, and let GPT figure it out. Have you tried anything interactively where maybe you pair ChatGPT with an interactive theorem prover, including error messages, and sort of let it sort it out?
Yes, this has been tried several times, and it does make a little bit of progress, but there are many things that it generates that is completely meaningless. So when you're asking, so the example that I tried most recently was asking it for a Misor proof of something, and it generates things that look meaningful, it's syntactically correct, but it introduces an intermediate definition, and then introduces a second intermediate, then a third one. After 60, it stops, and it has not made any progress. So that's a second class of things where it's not making progress and there's no error message to show. It is fine. It's a fine progress in the proof, but the goal has not changed so far. When it comes to the actual errors, for some of the errors, it can interpret what is meant by the error. Yes, the syntax one is fine. When it comes to type checking errors, fixing type checking around already functional programming is much harder than fixing it for imperative programs. So that's where I think we are still stuck even before theorem proving when it comes to type checking.
any more questions? Yes. And then, let's say, first over there, and then Phil.
Hi. So, what seems a bit weird to me when I look when I hear to the strategies for using machine learning to help through improving, it seems to me that these are very local techniques. That is, you look at your goal, you do some, I don't know, heuristic or neural network on the goal to evaluate it, whether it's good or not. And then, you decide to do something, or you decide to just stop and backtrack. But as a user of a proof assistant, it seems very weird to me because usually I have in mind where I'm going. I know why I actually did the few dozen of steps that I already did. And it doesn't seem that there's that this technique use this kind of history and long-term goal of proof. So I don't know. Is there?
Yes.
It's just complicated to do this, or?
This has been tried several times. So this is around these synthesis tasks where we are trying to conjecture some new things, and these new things can be completely new goals, but they can be intermediate steps in a particular proof, right? So you are trying to prove goal A, you have your axioms, but I'll first prove a goal B, and the synthesis of a sub-goal B is the thing that we believe has quite a lot. So I believe that it has quite a high potential. At the moment, all the things that have been tried are relatively weak. There are some successes. There are some even new things that have been proposed in a library and generalized, but they're still relatively few. So this can be done both in this conditional setting, so there's a final goal that I'm going to, and an unconditional setting, in the sense I have a library of 100,000 theorems in Isabelle, propose me some new goals that you would be able to prove, and that will be interesting for other users. And for this second one, we have about 5 that have been generated and proved and that are new. So some of those are generalizations of existing things, something that was true in a statement given by the user. There was a statement that was only true for square matrices, but the system realized, oh, it's also true for any rectangular matrices, and was able to prove it with a more general thing. Similar thing between continuous and Lipschitzian functions. So there are a few examples like this where it can propose something new and prove it. When it comes to the conditional setting, the setting that you asked about, where you are in a goal and you have something smaller in mind that's going to help you prove the goal, those are really, really very weak. But yes, this conjecturing is definitely something that's very interesting and exciting.
All right, so Phil, maybe?
Philip Wadler, University of Edinburgh. Thank you for the nice talk. We're talking a lot about putting various forms of machine learning into theorem provers. There's also the other side of it. So you touched on this, right? You said, oh, your ChatGPT has this little logic problem. We could solve it, right? So you need to do an output for that. So a couple of talks here have touched on that. David Harrell did a keynote yesterday where he used ChatGPT as a front end to his play-in-out system to do specifications of systems. And then when you had the specification, it gave you an answer because it was executable. Use ChatGPT to generate the output. This afternoon, Gopal Gupta and others are giving a talk where they have a restaurant recommender that uses ChatGPT as the front end, gives you formulas for answer set programming, it gets the answer and puts out. So this seems potentially very powerful. I'm wondering, is there a lot of work here? Are they ignoring it when they shouldn't be? What's going on in this area of trying to add various logical capabilities to GPT models or other kinds of models?
Right, so I know of several works in this direction. The one that I found most promising would be these tool-former models. So models where you have a neural network architecture where in the middle, it rather than just performing whatever convolutions, other transformations, it calls a sub-procedure. And this procedure that some people at the Polish Academy of Science have tried would be unification. In a similar work, you can actually run a SAT solver as part of your, so some SAT, unipropagation, so like propagation of things as part of your run, so encoding, decoding, and using it as a subpart, and train the whole thing using this as a subthing. This I find one of the more promising techniques. Otherwise, yeah, so the ones you've mentioned are pretty interesting as well, so yeah.
And is there a huge amount of work here, or is it very little work and we should be encouraging them to do more work? Do we just need to wait a year and they'll solve it all?
The AITP conference has people talking about this every year. There are maybe 10 presentations around this for the last few years, so I don't know. The progress seems to be there, but I don't think it's a year. I think it's more a decade or a few.
I'm not sure I can wait a decade. Okay, thanks.
Sorry.
All right, maybe one last question, and you can maybe set up in between.
Hi, Brendan Considine, McGill University. You mentioned at the end briefly about different foundations, and I was wondering if you thought about proof systems, tailoring the proof system to make it amenable to automated proof search. So maybe some have good metric structure as you're approaching the goal, kind of can tell you're very close, or have geodesics or short refutations, things like this.
Right. So when it comes to proof calculi that would be good for reasoning, is what I understand, for reasoning and for learning, what is the biggest issue is the branching factor. So the calculi that are more saturation-based and its variants in interactive theorem provers, so things like Auto2 in Isabelle, are the ones that are the hardest to introduce learning, where the space of actions is measured in millions and all these are equally probable. The calculi where the actions are smaller but you're making the decisions, and possibly there are these goals that we discussed, these intermediate goals, which is closer to the tableau-based calculi, are the ones where this works nicer. These are the ones which are also more natural for humans to analyze and to deal with. The issue with these is in automated reasoning, they're not doing so well with reasoning with equality because of completion and superposition calculus, the things you can do with orienting equalities. The Tableau systems are not the most efficient. But when it comes to logics beyond first order, we do not have extensions of that. So in this sense, I think going for the Tableau-based thing. So in this sense, something like BLAST in Isabelle and things around, so actually Auto and so on, are the ones that are the good ones.
Thank you.
All right. Well, thank you so much for this overview on how we use machine learning methods in automated reasoning and giving us some ideas on where we can use them. So